Well, guys, welcome to LispNYC. Tonight we have Rich Hickey. He's going to be talking about Clojure, and that's really all I can think of. Yeah.
Hi, thank you. I actually have a ton to talk about. It was very difficult to try to fit this into a 2-hour plan, so I'm going to try to go pretty quickly and handle questions either in bulk or at the end. But don't hesitate if you really are stuck on something to interject. Quickly, what we're going to be doing is this, an introduction. I'm going to talk a bit about the fundamentals because I know there's always a question when you write a new Lisp as to, why. And there are very strong motivating forces behind the design of Clojure. They reflect the experiences I've had, and I'm going to spend a fair amount of time trying to convey them first, so that when I describe the features, there's some context for that. So there'll be a rationale discussion where I'll tease you about some of the things, but hit on the points that underlie the design, and then I'll go through the features and show you a bit of the language, and I'll let you know where it's at and take some questions. My name is Rich Hickey. I'm just a regular old software developer. I've been doing it for about 20 years, 10 plus of C++ and plenty of Java and C#. And after that, Common Lisp, doing a fair amount of Mathematica right now. But I wanted to try to survey the room and see people's development experience. I presume Lisp, yes? Pretty much, but some, okay. How about Java? Okay, and how about functional languages like ML or Haskell? So, okay, we got 3 hands up from you. Okay. Mathematica. Well, it's interesting. Mathematica is pretty functional and not strongly typed, so it's an interesting. Erlang would be another thing I should have asked about. Clojure really touches on all 3 of these things, and it's rare for me to find somebody who knows all 3. So I'll try to fill in the gaps, but the talk will presume a lot of Lisp knowledge because it's just impossible to cover it all. So what are the fundamentals behind Clojure? One is that it's functional. That's a significant difference from Lisp right out of the gate. You can do functional programming in Lisp, but Clojure is really a functional language. Like the data structures are immutable, that kind of functional. So that's a critical thing that I'm looking for in a language now. I really want to write programs that are easier to understand, change, will work in the context of threads, things like that. Lisp is important to me, including down to the core principles of a very, very small core, this code is data principles, the notion of a reader, things like that. And so Clojure is a Lisp. It has all the parentheses and everything else. You'll see as I go through this that language being hosted, being part of an existing infrastructure is an important thing today, I think. I think that if your language doesn't run on the JVM or .NET, it's really at a disadvantage. And there are many, many advantages to being hosted. Most common Lisps sit on, sort of define their own world. Another fundamental of Clojure is that it supports concurrency well. And by that I mean mostly concurrency from a coordination standpoint. Systems I've written have mostly been automation systems, schedulers, some communications things, where inter-thread communication or sharing of data between threads is always the challenge. Less so the kind of concurrency, distributed concurrency, that Erlang would talk about. Erlang sort of unifies those 2 things, but Clojure does not. Clojure is about concurrency in proc. And Clojure is open source. All right, so why? Why do this? Well, it's very simple. I want these 4 things, and there's no language that has these 4 things. And I want them badly enough to waste a lot of my time doing this. Therefore, Clojure. All right, so we're looking for functional, we're looking for Lisp. I want it to run on the JVM and to be thread aware. So what do we like about Lisp? Well, Lisp invented most of the things that dynamic languages are still reinventing. and all those things are still good. But at the end of the day, in spite of the ascendancy of Python and Ruby, there are still some advantages of Lisp that haven't yet been copied. One is the fact that it's built on an extremely small core. When you compare Lisp to the current dynamic languages, they're full of syntax and fancy extra, what Lispers might consider superfluous characters and help. But the core is not small. Lisp's core is very small. And so the key advantage of Lisp, I think, that still remains, this is not to say that all the advantages aren't already there, but many of them have been copied. I mean, certainly garbage collection is pervasive, and a lot of the data structures have been copied, the dynamic nature, some of the meta programming capabilities. But the code as data, that notion of the source code for the language is a data structure, and that the actual operation of the compiler or evaluator is to evaluate a data structure, I think is a critical thing. And we know that that's the key to macros and syntactic extension. And with the syntactic abstraction, we don't need a language with a lot of stuff that the language designers put in, and we don't need to wait for the language designers to give us things. We can give them to ourselves whenever we need them. So everybody, I think, here that uses Lisp appreciates deeply that aspect of Lisp. So, of course, there are Lisps, and there are Lisps for the JVM. So why not those? I think there's a few things that made a difference for me. This is not to say anything bad about Common Lisp. I love Common Lisp. I spend a lot of money on LispWorks. I do a lot of development in Common Lisp. But as a language, I think I see these things that kept it from being the thing I would choose to solve the 4 problems I listed. One is that Common Lisp, for instance, is a standard language. Things that aren't in the standard are not in the standard, and there really isn't a process for a new standard. When I look at Lisp, the core data structures are mutable. If I want a functional language, that's not something that I want. Even though particular implementations have a story about concurrency, the language specification itself does not. It doesn't prohibit one, but it doesn't provide any guarantees. Whereas if you look at a language like Java, you see a lot of guarantees about how things work in the context of multiple threads and how memory synchronization works and things like that. There are already good implementations of the standard Lisps, and I think if that's what you want, I would definitely recommend them. ARM-Bear Common Lisp is a full Common Lisp that does a huge percentage of the test suite. Kawa is a scheme that compiles to bytecode, and Cisc is probably a more compliant scheme that's interpreted, but has good performance. And there are others. The last thing about the standard Lisps is that they do reflect an older design, which there's nothing wrong with, but it's an older way because there were no other choices, which is that a language is sort of its own platform. It solves all the problems for the developer, and in the end sort of becomes an island, and there's this foreign way to talk to other things. Again, I want a language that integrates with the standard platform for many reasons, which I'll talk about. So Clojure is a Lisp. It definitely is a Lisp. It has a REPL. It has code as data. It has macros, just like Common Lisp. It extends code as data to maps and vectors. There is reader syntax for those. Backquote works through them. They're completely, fully, and deeply supported. But it's straight code as data. The reader reads, the reader yields data structure, the evaluator evaluates and eventually compiles the data structure to Java bytecode. Clojure defaults to immutability. Most of the data structures, including lists, are immutable, which makes it a purely functional language with a lot of differences, both in style and approach once you start writing programs. The core data structures in Clojure are extensible. As we'll see later, that's another fairly big difference. Most Lisps, there's a whole suite of functions that work only on the actual concrete, cons cells. And they're hardwired to do that. And those functions will never work on anything other than that data structure. Most of the data structures in Clojure are defined by Java interfaces, and so that any algorithms that are written that interoperate with those data structures work on any implementation of those interfaces, not on a particular concrete data type. I'm sure people in Common Lisp have felt as I have sometimes, wow, I wish I could extend these sequence functions to my own data structure. And there really isn't a good story for doing that. And Clojure directly embraces a platform, not having any backwards compatibility issues. There's a unification of types that's pretty extensive between Clojure and Java. So Lisp is good. Functional programming is also good. I think that the functional programs, outside even when you start looking at concurrency, which we'll talk a little bit more about, functional programs are easier to understand and reason about, modify, test. And by functional programs, I mean most specifically programs that primarily deal with immutable data, that deal with functions that take arguments and return new values with no side effects. And two key aspects that are generally available in functional programming languages are this immutability and first-class functions. Of course, Lisp has first-class functions, and many Lisp programs are written in a functional style. And it's been a style for as long as Lisp has existed, but it's not enforced. So you can have a list, you can have the head of a list, and somebody could have promised you it will never change, but you really don't know that. And as programs get larger, it can be harder to maintain that stuff. Also in Lisp, only the list, the con cell, is structurally recursive. Hash tables, for instance, are not, and vectors are not. The data structures in Clojure are all structurally recursive, including the hash tables, which is kind of weird, but true. So I'll talk more about those later. Most functional languages today are strongly typed. Certainly Haskell and ML are way over on the strongly typed, and they have very sophisticated type systems. Personally, I haven't ever found them to work for me. I've had an afternoon when I worked with another senior developer, and we understood ML syntax, and we ran in our design into a wall. It could not figure out why I couldn't do it. And later I did some research, and it ends up we had encountered the expression problem, which is a known limitation of these type systems, and I don't think that they solve enough problems for me to make it worth it. Not to say they don't have any advantages. So Clojure is dynamically and runtime typed, not statically typed. So as a functional programming language, it's with Erlang that way, and not with ML and Haskell. So Clojure is functional, but it has a dynamic emphasis. Not only is it dynamically typed, but the data structures, again, they're immutable and they're persistent. And I'll talk more about what I mean by persistent data structures later. So they support recursion. Typing is dynamic, which means that you can have heterogeneous collections. You can have functions that return different types of values. I mean, people have been doing this in Lisp for a long time, and nothing terrible is going to happen if you say this function could return a string or an integer depending on what it's passed. If people understand that and it's part of the contract, that's okay. But those things can become incredibly difficult to describe in some strongly typed languages without constructing new types that represent unions of other types. And the last point about Clojure that makes it dynamic is a critical point, which is that Clojure really does embrace runtime polymorphism, the kind of polymorphism you get from interfaces in Java or from CLOS generic functions. That kind of polymorphism, I think, is critical to writing large systems that are flexible. And I find strongly typed things to become extremely brittle. Essentially, these pattern matches you do in ML or Haskell are really like switch statements, and they have that same kind of negative smell that switch statements have in Java. That it's brittle. You want to change it, you got to change the inside of this. There's no way to extend things independently. So Clojure has a unique support for runtime polymorphism, as we'll see. I talked a little bit about wanting to have a language that targeted a platform. And the theory behind that is this, that moving forward, virtual machines are going to be the targets of programming languages. It used to be that operating systems or particular machine architectures were the target of programming languages. I really don't think that's true. I don't think it's been true for a while now. But now it's become more formalized. Now you see .NET claiming that multiple language support, and the Java VM also does a decent job of providing a target for multiple languages. I think it's a very critical thing. When you look at these VMs today, and by that I mean the Java virtual machine, not VMware, they provide type systems with dynamic enforcement, safety constraints. They have security. They have dynamic code loading. They have huge sets of libraries. They have memory management and other resource management. For instance, garbage collection is a platform facility rather than a language, feature on these platforms. And in general, they all support bytecode and just-in-time compilation to machine code, which is very, very good. Some of the Java hotspot optimizations are stunning, quite good. So I think a new language should target a platform rather than reinvent its own bytecode interpreter, its own garbage collection system, its own set of libraries for doing things that are solved problems. Talking over the internet is a solved problem. Talking to a database is a solved problem. Redoing that in the dynamic language du jour, I think, is not a good use of time. But it's certainly the case that many languages are their own platforms. Then they define their own runtimes. Their own versions of all these things. I think, again, as I said, the new way is better. In particular, also my experience has been that clients dictate these platforms. I like Common Lisp a lot, but most of my Common Lisp development has been relegated to modeling, prototyping, design work, analysis. But runtime, production, it's a much tougher sell. These companies have big investments in the infrastructure, either Java or .NET. They understand the performance characteristics. They know how to scale it. They believe in the security of it. It's important to be able to target these things. If somebody said, "I wrote this great language, but it doesn't run on Linux," you'd say, what's the point of that? And that, I think, is the equivalent thing now. Huh? Or that. It only runs on Windows. How about that? That would make it really bad. So similarly, I think languages that don't run on these platforms are not appealing to a large majority of clients, and justifiably so. If I knew everything about how the JVM worked and I was pretty comfortable about it running on my servers, I really would only want to run languages that ran on the JVM. That makes sense to me. Java is a language plus a platform. It was always sold as a package. That Java means Java the language and this runtime that runs it. But there have always been other languages that targeted the JVM. Recently, Sun has started embracing them and saying, we want to support this. We want NetBeans to support it, and put a version of JavaScript in the JVM, the JDK, and things like that. JVM is pretty established, has a good trust level. It's now also open source. I think it's a good target. And that's why I chose it. Any language has always needs to interoperate with other code. Not everything's going to be written in your language. It used to be a C interface was the primary necessary way to leverage legacy code and code other people wrote that you don't want to rewrite. I don't think that's really the dominant linkage required today for languages. I think access to either Java or .NET is the foreign function interface you require. So Clojure is a language, and it really looks at the JVM as a platform, supplying these services. Another key design point of Clojure is that object orientation is not that great. I think that it was born in simulation contexts, and by object orientation in particular, what I'm talking about is stateful object-based systems, where you have a bunch of objects that have state and they talk to each other and change each other's state. Languages like Java and C#, it's almost impossible to do something else. We have some shops where we understand functional programming and want to do more functional programming and encourage developers to do it, and it's really hard to do the right thing in C#, for instance. It's not idiomatic, it looks weird, and developers don't really get it, there's no data structures to help you. It's very hard to write programs that take arguments and return new values, which is kind of a shame. So I think mutable stateful object systems are spaghetti code. That's just dressed up, but that's what it is. And I'm tired of them after 20 years of making them. They're hard to understand, hard to reason about, and for concurrency, it's very difficult. I wrote highly concurrent audio playback systems in C++ with locks and semaphores and mutexes, and it's really, really painful. Also, I think that there's a tendency to think that inheritance is equivalent to polymorphism. That's what polymorphism is, and that's not the case. Clojure has a runtime polymorphism system that's completely independent from inheritance and types even. So I like polymorphism, but I don't think inheritance is the only way to do it. So I like polymorphism. Basically, either switch statements. I mean, everybody's been told this in Java. If you have this big switch statement, if it's a this, do that. If it's a that, do that. You really should have a virtual function and make a hierarchy and make this polymorphic, and because the other is brittle. And I also think that the structural matching in Haskell and ML is also brittle. And I think if what you're doing is writing a theorem prover or a program that's essentially mathematical, that kind of brittleness is okay. But if I'm writing a content management system, I don't want to have to down it, rebuild every single piece of it because there's a new kind of content or media. That makes no sense to me. I want programs that are runtime polymorphic. So I think that's good. There are ways to do it in the different languages. Clojure takes away an approach that supports a couple of things that I think are critical. One is there are, in my opinion, no polymorphism systems that really support multiple taxonomies well. And by multiple taxonomies, I mean, it's easy to decompose your system and say, well, there's shapes. My system is a graphic system, and there's shapes, and so there's shape, and then there's circle and triangle and rectangle, and I can decompose the system that way, and I can make a hierarchy in Java or in CLOS, and do that. But if those shapes are also entities in the game, and some of those circles are also shields, and some of those squares are also walls, I can't have another taxonomy, which is their role in the game, and do that effectively with types, even with multiple inheritance. To have the round, shield, expensive, blah type, it makes no sense to me. And they're never dynamic. In reality, we classify things. We do, but we classify things by their dynamic attributes. Right? None of us are born fathers, best friends, programmers. Yet these object-oriented systems, that's what they want you to decide. What is this object? We're going to determine everything it can do when we write the code the first time. So Clojure's multi-method system is polymorphism that's not really tied to type hierarchies or that, and therefore it supports multiple taxonomies easily and can dispatch on dynamic properties of objects. And then the last motivating thing here is concurrency. Most of the systems I've worked on have been multi-threaded systems, again, in C++, Java, or C#. They're very hard to get right, especially once you have objects whose state can change and you're trying to share them. Manual locking is extremely difficult. Making your data structures immutable works really well. I don't know if anybody's read Java Concurrency in Practice or whatever it's called, which is a fantastic book. I highly recommend it. It lets you know how hard it is to do concurrency in Java, which is a language that has a lot of support for concurrency and a lot of well-defined semantics for behavior in the context of multiple threads. But it's still really hard. But one of the pieces of advice is, well, if you just make your data structures immutable, all these hassles go away. So you don't need locks. You can share them between threads. And you do get a lot out of that. And that's why that's the default in Clojure. But real systems, including simulations, and almost every system I've ever worked on, needed to have state that changed. So Clojure is not a purely functional language. It doesn't relegate changing things to some evil monad or anything like that. But it has very well-defined places where you can change things, and it has two distinct ways it supports having things change in a program where there are multiple threads, and I'll talk more about that later. So locking is really hard. And really, every time you do it, you have to do it over again. There's almost no way to sort of encapsulate locking patterns in languages like Java. They just don't have the syntactic extensibility to even do that. But the fact of the matter is, if you write a program, and at a point in the program you need to change 3 distinct things, you have a really difficult problem. And if you have 100 things and you need intersecting sets of things you need to lock at various points in time, it's really almost impossible to do well. So Clojure has what's called a software transactional memory system that automates that locking as if it were things like database transactions, and I'll talk about that more. So that's a pretty long-winded why. And so now we can talk a little bit about what did I actually do. And it's basically the same points. I'll show you dynamic development, how Clojure is a Lisp, how it supports functional programming, the multi-method system, the software transactional memory system, and the Java integration. Does anybody have questions at this point? Am I going too fast or too slow? Okay, no complaints.
Just right.
Well, say it's fine. So dynamic development, I kind of left this part really short because I felt in this audience everybody's going to yawn about this. Of course, we know REPLs. We expect languages to be able to walk up, type something in, try it, define a function, try it, leave the data in memory, change it, fix the function, run it again. Something other than compile, run, fail, get the log, edit the code, try again, maybe run a debugger, that kind of experience. So Clojure supports the interactive experience of Lisp. Maybe I should just show you that Clojure exists before we... Right, so we have Clojure here. I can't actually see my screen, so there you go.
Yay.
We can look at the system. So it's what you expect. It's not a particularly great REPL, I would say, right now. But it is a REPL, and it does what you expect. Clojure has all the basic, literals for arbitrary precision integers, strings, ratios, doubles, characters, symbols, keywords. Some of them are a little bit different from common Lisp, like keywords aren't symbols and little things like that. But the basics are there. In particular, what Clojure has, which is unique to it pretty much, Kawa has it, is dynamic compilation to bytecode. So when you're in the REPL, it's not interpreted. There's no interpreter in Clojure. It only compiles. So you type anything in other than, if you type in X, I look up X and give it right back to you. I don't make any bytecode for that. But anything non-trivial gets compiled to bytecode. All function definitions always get compiled to bytecode, and they get compiled to bytecode right away. And then you have compiled JVM bytecode running from then on. And it does it dynamically. It never touches the disk to do that. So it's a dynamic programming language that way. It is in many other ways the ways you expect Lisp to be. It's a Lisp. There's a lot of things that make something a Lisp. It doesn't have C loss, so it doesn't mean it's a Lisp that way. But it means it's a Lisp in the way I think is still, like I said, the critical thing that distinguishes Lisp from Python and Ruby and these other languages which have tried to catch up, which is that code is data, that the textual representation of source code is not what the language is defined on top of. The language is defined on top of data structures. And the reader will read pieces of text and create those data structures, but the language is not defined in terms of the syntax of particular characters or strings of characters. It's defined in terms of data, which means that macros are supported. As I said before, Clojure extends the reader of Lisp. It has parenthesized X expressions, and they are exactly what you expect. But it also extends it to maps and vectors. And I think it does that. I think that's important. I think it's important in a way that modifying the read table is never going to give you. For instance, it's hard to modify the read table and have backquote work through your reader stuff, if you've ever tried that. And I think it's important for any language to provide an ability to read in maps, literals. If you want to say, well, we don't need XML, we have S expressions. Well, you need a literal way to write maps. I think it's just not acceptable to not have that. And in fact, languages like JavaScript have that. So it has that, and it has macros, and they're common Lisp style def macro programmatic macros, not scheme style pattern generator style macros. Clojure is a Lisp 1. So as a Lisp 1 with def macro, there are some issues there because you have these problems with name aliasing. And Clojure has worked hard, I've worked hard in Clojure to avoid those. And the way I've done it is by having it be a two-step process that symbols are distinguished from places. And by doing that, you can have simple, unadorned, package-free symbols. And that's what gets read by the reader. And during the evaluation process, they get resolved. And by making it a two-step resolution process, you're able to have def macro style macros in a Lisp 1 and avoid a lot of the incidental aliasing, particularly of function names, which is the main argument for Lisp 2. I like Lisp 1 better. I like evaluated function position. Yeah. Yes, it is. Yes, definitely. So here's an example of a macro. It doesn't look too much different, except you're seeing a taste of the fact that Clojure supports overloading by arity directly in the fun, which is Lambda. So end here has got 3 versions which are overloaded on arity. And ampersand, whatever, is a rest argument. No keyword arguments, no optional arguments. But it supports true overloading, and it supports extremely efficient overloading. This yields 3 entry points in a Java interface, and when you call it with 2 arguments, you don't get a conditional running. If it's 2 arguments, do this. You get a direct call, 2 arguments on the stack, to a 2-argument function. So this is not just syntactic sugar. This is fast stuff. And that's why I bothered to do it. Functional programming, of course, this is not unique to functional programming versus Lisp. I just had to put it on one slide or the other. First class functions, there's your classic make adder, make a function which adds something to its, takes a number and makes another function which adds that number to its argument. So that looks, defun is defun, it's just missing the U. Square bracketed things are vector literals. So the reader reads that, that's really a vector. Let also takes a vector. And in most cases, things that are not calls, either calls to functions or to macros or special operators, use vectors as syntax rather than lists. So that most lists delimit calls, or the definition of things that become calls. It's a stylistic thing. Some people do this in Scheme now, where schemes treat square brackets as parens, and they just do it to help distinguish the code. In Clojure, square bracketed things are vector, are read as vectors. Fun is Lambda. So we return a new function that adds x to whatever we've been passed. And then we can define an add to function by calling makeAdder and do it. So def sets variables in the global var space, which I'll talk about later. Defun also does. So add to and adder both look and feel like functions. And as you saw before in the macro definition, it's the same story for functions. That fun, lambda, fun, and defun therefore support the definition of multiple argument, multiple arity functions. And this is really important, I think, because it's very difficult to support optional parameters and keyword parameters efficiently in a single function object, because you pretty much have to do conditional code in a lot of cases. Or know more about the call sites. I mean, you can, in certain call sites, do something better, but not generally. This way, you end up with function objects that really have multiple entry points, and you can pass them to anybody and have no idea how they're going to be called. But when they get called, again, as I said, if they're passed 2 arguments, this this version will be called, and there's no conditional branching associated with that. So it's nice. So you end up with function objects you can pass around that are variadic, and not just taking rest arguments kind of variadic, but really have multiple argument signature lengths. Obviously, optional parameters are a little bit more succinct. This is more general, though, in my opinion. So we've seen some code. It ends up that all of these things you've seen. I mean, you've seen already functions being defined, lists delimited by parenthesis, regular access expressions, vectors delimited by square brackets. Here we're seeing. You see my? Oh, good, you do. Here we're seeing a literal map, which is basically pairs inside curly braces, key and value. Keys and values can be anything. Any of the Clojure data types. You can have maps as keys. You can have vectors as keys. It really doesn't matter. All the types support value-based equality semantics strongly because they're immutable. They can. So if you've ever read Henry Baker's paper on equals, this is egal that he talked about in that paper. Real equality. Yes?
Map's just a hash name, right?
Map's the name of a let variable.
Yeah.
It's a local.
Okay, so it's not the function.
No, there is a function called map.
Okay.
And it's a list one. And this is not a problem because of the way symbols work in Clojure. So yeah, I couldn't actually call map in this function if I had the variable named map without a qualifier of the package. But it ends up being the best name for this context, and I'm not going to use the map function in this function. So just so you know, we're not calling function here. This is a regular let. There's no extra parens, so the pairs aren't extra parenthesized. Generally in Clojure, most extra parentheses are gone. They're gone from cons. They're gone from let. So we have a vector with a vector literal. We have a map mapping a string to a keyword value. We have a list. Well, here's an example where I didn't use the word list, the symbol list, because I want to use the function list, which is a lot like scheme. And I think that's the only real negative about Lisp 1, which is I can deal with. And then we're going to make, the return value of this is just going to be a list where we're going to modify some things. So conj is like a generalized version of cons. What is cons? Cons is put a thing onto a list. It ends up meaning put something onto the beginning of a list. Conj in Clojure is that, except it works for all the data structures, and it puts something onto the data structure in the way that makes sense for that data structure. So when you conj onto a vector, it goes at the end, because the vectors are expandable at the end. If you conj onto a list, it goes at the beginning. It's in fact the same as cons. There is also cons that only works on lists. For maps, I could conj on a pair of key and value, but the main way you manipulate maps is with the assoc function. It doesn't mean at all the same thing it does in Lisp. Here it means associate this map, associate in this map this new key value pair. And what it yields, in all three of these cases, these yield new data structures. It yields a new vector, the same as the old one with 5 at the end. It yields a new map that had Fred and Ethel in it and now also has Ricky and Lucy. It yields a new list with 5 on the front. And then we can also put the originals in this list to see that they're the same. They didn't change. So there's no real mutating functions. You can add things to vectors like they were expandable, and you can add things to maps, and you can push things on the beginning of a list. But just like when you push something on the beginning of a list, you never really change the list. That's true of vectors and maps too, in Clojure, because they're all immutable and they all share structure, which I'll show you later. And so what do we get back? We get the new vector with 5 at the end. The new map, you can never tell the order you're going to get here because it's just associative. And this map is actually a hash map. The map literal yields a hash map, not a tree, for instance. Although I do have red-black tree data structures in Clojure. And there's the list, again with the 5 at the front, because that's what happens when you conj onto a list. And there's the originals down here. So everybody got this? Yes?
Are you allowed to say conj 5 vec?
Conj 5 vec. No.
Okay.
No. Some things can work either way, like lookup can. Lookup, keywords are functions of maps, and maps are functions of their keys. So then you can, but conjing is always collection value.
And I don't understand what's on the bottom.
Cons is the other way though, so people wouldn't go insane. Cons is value list. Excuse me? The bottom is the result.
Okay, it's all
In a list.
Oh,
I asked for a list of all these things, and this is the return from that. And this stuff is all there. I can't see my screen. I'm sorry. So that's a real thing, and I can say for that thing. Get me A. So, these data structures are just like lists. You can use them the way you're used to using.
Notice it with comma.
Yes, commas are white space. Because I took out a lot of the extra parens. If you have a really long list of unparenthesized pairs, it's easy to sort of lose your way. So if it's convenient to you or it makes sense, you can add commas. They're white space, which means I used a different character for unquote. Okay, I've said persistent data structures a couple of times, and usually what that conjures up in people's minds is something about, they could be stored in a database, because that's the dominant notion of persistence. But there's another meaning of the word persistence when it comes to data structures, and that has to do with them being both immutable and able to provide what are quote-unquote modification operations that are efficient, that aren't copying. You're used to that with Lisp. Lisp lists are persistent in that way. When you add something to a Lisp list, it shares structure with the list it was added to. It's a different list, right? It's got a different head. It's a different reference. But it shares structure with the original list. And you can have multiple lists that share tails. That notion of being able to change something or add something to it or remove something from it and maintain whatever the efficiency guarantees are of that data structure across those changing operations is persistence. So typically, hash tables or vectors provide certain efficiency guarantees in the behavior of adding things. For instance, lists, adding something should be, big O1 to put something on the front. The cost of it is not related to the length. It ends up vectors in Clojure make the same promise for conjing something onto the end. It's big O1. But that means it can't have copied the whole list in order to do that. The whole vector in order to do that, because that would be big O(n) to make a whole copy. So all the data structures in Clojure are persistent that way. They're immutable and they can be efficiently modified. For lists, that's pretty easy. Also, trees are also easy. They're pretty much the traditional functional programming language solution to maps. Most functional programming languages have a good red-black tree implementation that's purely functional and is efficient. Its behavior is generally log n for insertions and removals. My experience working in C++ and C# and Java on programs is that something without much better than log n time is required for real programs. I mean, everybody that uses Common Lisp knows the value of switching to a hash table when you need it from an association list, for instance. So I worked very hard to provide the two data structures that are extremely gnarly to do in a persistent way, which are hash tables and vectors. It ends up there's no way to get around some sort of tree-like data structure in order to share structure. But there are much more efficient ways to do it. These data structures are log base 32 to the end, which means if you have a billion things, it's a 5-step process max. So to me, that's like big O1. That's close enough. It's a lot different from, say, a red-black tree where that's now 32. for the same, or 30 for the same data structure size. So they're very clever things. Bagwell invented this array mapped hash trie data structure. His wasn't persistent. I guess my 2 cents was to make persistent versions of these and to use them for vectors and maps. I'm pretty happy with these. The insertion speed obviously can't compete with, say, Java hash map. But the lookup speed I found in some cases to be better because you have much better cache coherency with these array map tries than you do with like a big table-based hash table. So the lookup speeds are excellent and very competitive. And I'm thrilled because this now means that immutability is practical from my perspective. And there is also a sorted map, but which uses a red-black tree. So you've got the basics of real programming tools there. A critical aspect of Clojure is that the abstractions are extensible. I sort of mentioned this before, but I think it's something I can't stress enough, and it may be hard to get a grip on. And that is that there's a lot of code. There's code in Clojure that manipulates sequences, a lot of it. All the kinds of things, map and fold and reduce and filter and those kinds of things. Those functions are written in terms of an abstraction, not a concrete data type. And all of the data types I've shown you have representations as Java interfaces, as abstractions, which means there can be multiple implementations. In fact, there are 3 implementations of hash maps. One for when things are very small, one for when things are medium-sized, and one for when things get arbitrarily large. You can start with one, add enough to it that it becomes the other because you're getting a new thing back each time. Nothing is built to the concrete types. Everything's built to the interfaces, which means that at a core level, if you had a serious performance problem you wanted to address, or you had a really unique new kind of data type you wanted to integrate with Clojure in a deep way, you have a path to do that. You have these interfaces, you can implement them either in Clojure or in Java, and the library function is going to work with the things that you write. That's not true of, for instance, the built-in functions in Common Lisp library. I think it's a big improvement over hardwiring a language to its data types in a concrete way. And it's used throughout Clojure. In fact, even invocability is an interface, which I've leveraged many times. For instance, there are function objects, but they're not the only things you can call. You can call maps. Maps implement the invocable interface, and they're functions of their keys. So let's look at this in a very concrete way that I think would make a lot of sense to a Lisp group, which is that cons is not primary anymore. And all the functions that were written in terms of cons and car and coulter now are written in terms of first and rest, which are just renames, which are functions and are part of an abstraction. Is there an actual slot for the first thing? You're not going to know. You're not allowed to know. Is there an actual slot for the coulter? Not going to tell you. There are these 2 functions. Implement your algorithms in terms of these 2 functions, and then other people can implement data structures that implement these 2 functions, and the 2 things are going to work together. This is, it doesn't seem that novel now because Java and C++ and C# and all the languages since that stuff started to happen do this normally. But back when Common Lisp was invented, that kind of abstraction was not common. And in fact, all of CLOS happened too late to be the way all the functions in the library were done. And there, CLOS being a way to do these abstractions. There are many implementations. And also, the sequence abstraction could be lazy. There may not be a rest until you ask for it. And in fact, most of the sequence functions in Clojure are lazy, like Haskell kind of lazy. Like you can write functions that return infinite lists, no problem. So they can have many implementations. You're not limited to a particular implementation. So seek is the thing I call cons. Seek is an abstraction. There is a cons object that's used to implement lists, but it's one of many things that implement seek. All the collections can provide seeks. You can additionally get a seek object, an object that implements this interface, over Java iterables, which means all Java collections, and Java arrays, which means all of the Clojure functions, map, filter, reduce, all those things work on all of these things. Work on all the data structures, work on all the Java collections, and on Java arrays. And everything you write that calls first and rest will also work on those things. So I spoke a little bit about how REST could be lazy. And in fact, lazy sequences are an important part of the design of the library. This is where Clojure probably takes a strong hint from Haskell. Haskell's always lazy. No values are produced until they're needed. That ends up yielding a whole other kind of programming. And that wasn't my objective, but I certainly saw the advantage to doing sequences in a lazy manner. You can now work with arbitrarily long things, and they can get generated on the fly. You can write algorithms that speculatively pursue spaces that don't ever have to really be realized until you look into them. And it yields a very elegant style of programming. So there is a primitive inside the implementation of Clojure which implements that sequence interface lazily, which means it has as its REST argument a function, and it will call it only if the REST is called for, is asked for. And that's exposed in Clojure through a macro called lazycons. And lazycons, puts some actual value on the front of an expression. This expression is not evaluated now. It's packaged up in a Lambda and stored away. And only if, when somebody uses this, do they call for it, do they get it. So this is the take function. This again is more Haskell-like. It says, give me the first guy, n guys from a sequence. So it takes n in a collection. It says if there's, if I still have more stuff to grab, and the collection is not null, I'm going to return the first thing in the collection, lazily consed onto taking one less from the rest of the collection. So this is nice recursive style function definition, except the rest of this doesn't actually happen now. And it may never happen. If I say take 50 things from this, and then I start walking through it, and I find the thing I want in the first 5, the other 45 are not ever generated. And that's true of all the functions. There are a ton of sequence manipulation functions, and all the ones that produce sequences are lazy. They produce sequences lazily, and you can too. So here's an example. There's a function in the library called cycle. It returns an infinite sequence of whatever sequence it's given. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And we can go and say take 15 from that cycle, which is infinite. Now, of course, you don't really want to call cycle on the REPL directly, because that will go forever. And so you have to be careful with an interactive language like this to do that, not do that. But that's an example of the kinds of things you can do. You can write functions called prime numbers or Fibonacci numbers or even numbers that are infinite, and then use them as you need. Yeah.
So the only reason, is this correct? The only reason that all 15 get generated is because it's being printed.
Exactly.
Yeah.
Because it's being printed, it runs through all of them.
If you had another take that said just take 5,
The others would never have been generated. Right. And that goes on and on. It's deeply lazy. All the functions are lazy. Yes?
Does this mean you get a compile step for each member of
No.
the sequence that you actually generate?
No. It's a lambda is generated that wraps this, and that's a compiled thing. It's like when you compile a local function in Lisp. You get one compiled version. A new instance of that compiled function is generated each time, but no new compilation occurs. Yeah, question? Okay. I think this stuff is cool. It's something I thought was really impressive about Haskell, because some of the algorithms are incredibly elegant, and they're very efficient, because you really don't use more than you want. I mean, you think about how many times in Lisp you're like, I don't really want to do this because then I'm going to have this whole big thing, and then I might have 2 whole big things, and I might run out of memory. Now those algorithms become simple because you don't need to even think about that. You're not going to generate anything you're not going to use. Clojure has support for metadata. By metadata, I mean information about data that's orthogonal to the data itself. I find in systems I've built that a lot of times I want to know there's this thing I got. It's the data structure I care about. But where did it come from? What database table did it come from? What calculation is the result of? Has anybody looked at it and said it was okay? Do I trust it? How old is it? Now, typically, those kinds of things, information about the data, in most programming languages, you're like, I don't know where to put this. And you end up extending your data structure with stuff about last edited date, origin, last validated. And this stuff is not really your information anymore. It's stuff your program needs to know, but it's not the information. And there's no good place for that. It ends up that there is no good place for that unless your programming language says, I'm going to give you a place, and this is where it can go. And so Clojure does that. All symbols and all the collections have a meta slot for metadata, and that holds a map of metadata. It can be empty, and it is by default. But it gives you a place to store information about the data. In particular, that information is not part of the logical value. So, for instance, it doesn't impact equality. I can have a vector 1, 2, 3, 4 and another vector 1, 2, 3, 4. This one's from Fred. This one's from Ethel. Are they equal? Yeah. They're equal. Because them being from Fred and Ethel have nothing to do with their logical values. So those two things are separate. Information about the data and the data itself. And that goes all the way through. Doesn't impact equality. It's not seen in operations on the value. There's support for literal metadata in the reader, so you can write metadata in code, in data, directly. And of course you can do it programmatically. Here's a vector 1, 2, 3. I'm going to just attribute that vector with metadata and add that trusted source map. So this attributed vec is the same value as the other vec, but it's got metadata on it. The caret here is a reader macro for meta. It just turns it into meta of attributed vec. So I'm saying, get me the metadata of the attributed vec. And keywords are functions of maps. So this says the source of the metadata of attributed vec, which is trusted. So keywords are functions. That's very handy when you use maps. It allows for very easy to read code. This is just, again, reader, syntactic sugar, read macros, the same kind of stuff from Lisp. But then I can compare these two. One has metadata, the other one doesn't. And they're equal. Anybody have questions on that? Yeah.
Earlier you showed the map as a function with the keyword as the argument.
Yes,
So
they're both
directions.
Keywords are functions of maps. Maps are functions of their keys, whatever type of key it might be. But strings, for instance, aren't functions of maps because I didn't write string. Clojure strings are Java strings. So keywords have a special extra capability to be on the other side. But maps are functions of their keys no matter what they are. Keywords happen to be functions of maps. They presume if they're the function, the argument is a map. And they'll look themselves up in it. Which is really neat. But it means also so that there's no aref. If I have if I have, So vectors are functions of their indices, for instance. So I have a vector, I'm using it as a function. You won't always use these things, but they make sense. And there are places where they make the code quite elegant. Oops, did I go ahead? Yeah, okay. So, looping. I have two problems in Clojure. One is I took away my mutable local variables. Like you've seen a bunch of lets. Those things that you let, you can't change later. There's no set of locals. You can't change locals. So I lose my counter ability in looping. The other problem is the JVM itself does not support tail recursion. And there's some approaches to language design where they just say, all right, well, especially if you're implementing a standard language that requires it, like Scheme. You sit there and say, well, I have this problem. The standard language says I have to have proper tail recursion elimination, and therefore most of those schemes either are interpreted or they invent some other calling method that's not the native one. That's sort of against the grain of Clojure, where I want my calling sequence is the Java calling sequence. I push args, I call a virtual function. I'm as fast as Java calls, which means I'm stuck with Java's ability to call functions and Java stack architecture, which means I can't actually implement tail recursion optimization on the JVM, which leaves me stuck because I really, that's elegant and that's functional and that's the way you should do it. So instead, what Clojure does is it has only local recursive looping, and it does that through a special operator called recur. So this is worth explaining a little bit because it's kind of weird looking. But the bottom line behind recur is actually pretty simple. And it's a lot like do from Common Lisp. If you ever read the spec carefully, do is defined in terms of rebinding. It really is a logical rebinding. And of course, that means it could have been implemented in terms of a call to Lambda. But it never is. It's the theoretical, Lambda calculus view of things. Similarly, recur is a rebinding piece of syntax. And what it means is rebind the arguments to recur to whatever they map to, and I'll show you how that mapping works in a second. And then jump to the nearest enclosing either loop, which is another special operator, or the function frame. So loop is exactly like let. In other words, it establishes bindings and then executes its body. The only difference about loop is that if there's a recur inside it, it goes back up to that loop. If this was a let, the recur would go back up to the function entry point. So recur will rebind the arguments and go back to the nearest loop, or failing there being a loop, the nearest function frame. So this allows you to write recursive looping algorithms that do not consume stack space. So this is a zero stack space consuming loop. So loop has 3 values that it binds, which means that the accompanying recur also has to supply 3 values. So in the recursion, map now becomes this, ks becomes that, and vs becomes that. They get rebound. And then execution comes back up to the if and goes through again until eventually, hopefully, you've written the termination condition where you don't keep going, and we return the map. So the purpose of this is, it's like all the functional programming languages have zip, or take 2 lists and return a list of tuples of the pairs. So that's not really that useful in Clojure because you really have maps. So this is zip map. Takes keys and values in 2 separate sequences and puts them together as a map where each key is mapped to the corresponding value. And this is a nice recursive loop. You would do, let rec or named let in scheme is a lot like this. This is actually a little bit more succinct than that. One of the neat things about it, it's a sort of an apology, because I'm not claiming it's as generally useful as proper tail recursion. I can't do proper tail recursion. But one of the neat things is that I do check that the calls to recur are made in tail position. It's a common error in scheme to use a named let and then try to call it, and it's not in a tail position, and I wonder, why am I blowing stack? And everybody, and you see it in the news groups over and over and over and over again. People, have this error, and people say, well, it's not really in the tail position. So you can't actually put a recur statement in non-tail position. You get a compile error from that. Yes.
I'm out of curiosity, do you implement this the same way you were implementing like lazy cons?
No.
It's a totally separate mechanism?
It is a bytecode goto.
Okay.
It's a real loop.
Okay.
This is a real loop. No lambda, no wrapper, no nothing.
Mm-hmm.
This is no dynamic memory allocation, no stack consumption for this loop. It's a goto. Yeah.
Is Java ever going to get real time?
Unfortunately, there aren't enough Lisp-like languages. I'm in the JVM languages group, and the guys who write JRuby and Jython and Groovy, they don't seem to want this because it's not a stylistic convention of those languages to do looping this way. They all have imperative loops. So there's not enough people jumping up and down. But I do think that the guy who does the hotspot thing, who's on that group, is extremely aware of the kinds of things that proper tail recursion, elimination, optimization allows. And so it's on the table. I think the main issues have to do with security, because you blow out a stack frame and therefore you could blow out some security context information that you have. That's always been the argument against it, but I think people have solved that problem in research, so it's a matter of working that into the practical JVMs. Okay? All right, so I've said a few times I think runtime polymorphism is really, really important. And so to boil that down really quickly, what do we mean by runtime polymorphism? We mean there's a function foo, and when you call it with different things, different actual functions get run. Okay? In Java, that means you call a method of some interface, and then at runtime, when you really call that method, you may have different classes that implement that interface, and therefore you get different actual methods run, depending on the arguments to the call. CLOS, it's the same thing, except that's now multi-methods. So more than one argument can participate in it. Also, it's not just about type. You can also have equality comparisons in CLOS. Right? When I look at this problem, what I see is this. All polymorphism like this is a matter of indirection. Right? You say foo, somebody looks at the arguments, gives you a particular method of doing foo. Right? In Java and all single inheritance languages, you say foo, they look at what get class of the thing, there's a single slot for foo, you get the version that corresponds to your class. Okay? CLOS, you say foo, A, B, goes and looks up in their multiple dispatch mechanism, whatever CLOS is going to do for you, figure out, based around either the types or the values of A and B, which method to use, you get that method. Right? That's generic functions. But generally, the problem is this. You have some set of arguments, you have a function on the arguments that determines what method to call, and then you call that method. That's what Clojure implements. So it's really a full generalization of indirect dispatch, and it's not tied to object orientation, derivation, types, or anything else. The way it works is when you define a multi-method, the one thing you're going to supply when you say, I'm going to have a multi-method called foo, is a function called the dispatch function, which says, this function is going to look at the arguments and return a value. That's the function I'm going to use to determine how to dispatch. I'm done defining foo, the multi-method. Now, I want to define a method for doing foo. I'm going to provide a mapping of a value, return value of that function, to a particular method. Okay, so there's a dispatching function, which is called on the arguments. It can look at all the arguments, one of the arguments, the third argument. I don't really care. It can look at its types. It can look at its shoe size. It can look at its metadata to see how old it is. I don't care. It can look at something that's going to be different every time it's called. I don't care. What's going to happen is that function is going to return a value, and somebody's going to have defined, hopefully, a method that says, when that's the value of the dispatching function, do this. Which means if you want to implement object orientation, in Java style, well, that function is get class. And when you write methods, you say, when this class is called, this is the method. When that class is the result, that's the method. And there you've got single inheritance dispatch. Similarly, you can do CLOS style multiple dispatch on types. But you can do dispatch on anything. You can do dispatches on values in particular keys of maps. That means that you can do multiple taxonomies, because maps can have all different kinds of keys. I can have a key that is my shape, and I can have another key that is my role in the game. I can have different, multi-methods that dispatch on those different pieces of the objects. I don't have to define circular, shield, expensive, whatever type. So the call sequence is this. The dispatch function, which was supplied when the multi-method was defined, gets called on the arguments, gets past all the arguments. It can look at them, any part of them. It returns a dispatch value. The dispatching mechanism then takes that value and sees if there's an associated method. If there is, it calls it. There's a way to define a default method so that would be called. And then if you don't define a default method, you'll get an error saying, I don't know how to do that for those arguments. So let's look at that to make it a little bit clearer. So I'm going to define a multi-method called encounter. And here I've done something very verbose, but a lot of these multi-methods become very easy. You can supply a function that already exists. Here I'm defining a function on the fly, and this function, the dispatching function, is going to take 2 arguments, and it's going to pull out the species of each argument and return that in a little tuple, a little vector. Okay, so the dispatch function of encounter takes the arguments, pulls out the species of each argument, and returns that in a little tuple. Okay. Now, so that's def multi. You do that once. You say there is a multi-method called encounter, and this is how it generates dispatching values. This is the dispatching function. Then we can define a method of encounter. Well, when the dispatching function returns a bunny and a lion, this is what happens. When the dispatching function returns a lion and a bunny, this is what happens. Similarly, this and that. Okay, you could do this with CLOS multi-methods, because this is just looking at effectively if species was the type. But I didn't make species a type. In fact, I don't have types like that. You could imagine that these things had other things, like whether or not they were carnivorous, or their color, or any other kind of taxonomy that you want to apply to bunnies and lions. This one is about species, but other stuff could be about other parts of these objects. So we define a bunch of methods. They just return keywords now. Then we're going to define some animals, 2 bunnies and 2 lions. You can see species bunny, but there's other stuff in these things. I don't care what it is. I don't care. I mean, they don't have different types. They're all maps. I don't really care about types. Types really, they don't make this any easier, faster, or anything. This is better, in my opinion. So what do? We encounter bunny and bunny. They mate. Bunny meets a lion, runs away. Lion meets a bunny and has dinner. And 2 lions meet and they have it out. So this is a simple example. But this is an extremely general system, and it's pretty easy. Just define a function, or supply a function. Your function could be first. Your function could just be the keyword. Like if you just want to say dispatch on the species of one thing, I could have just put as my function :species, because that keyword is a function of whatever it's passed. So doing things that are that simple are that simple, but doing things that are pretty involved, like, for instance, there's no reason why this function couldn't compare these 2 values and perform some logic on them, like if the second thing is greater than the first thing, return G for greater than, or GT. In other words, arbitrary logic can run in these functions. It's not limited to types, values, slots, or anything, or equality. It could be any arbitrary function of the arguments, which means you can also have some dispatching methods that just look at the arguments and say, this is an error. I'm just going to throw an exception. Because this shouldn't, this second argument should never be greater than the first. So it's a way to also do constraints. Did you have a question?
Here, in this case, they all match one single method, right? But if you had defined methods that get matched, I guess more than one of those encounters.
No, you can't.
Oh, okay.
Right.
Okay.
No, you can't. Right. It can only end up yielding one of the values, and the values are matched by equality. And of course, that also proves that vectors, for instance, support equality. You can use vectors as values. These are like little tuples. Yes?
On this, can you have variable length lists? Like, could you just have bunny and then bunny and lion?
You can. What you need to be able to do is to make sure that your dispatching function can handle whatever arguments might be passed to the others. So there isn't a straight conformance requirement like there is in CLOS. In fact, it would be possible to have multiple versions, some which have more stuff. But I need to make sure that my encounter thing, even if it didn't examine anything beyond X and Y, could take it. So for instance, if I wanted to have bunny, lion, and maybe a third thing, and sometimes that third thing matters, I'd have to make sure I had an end I don't care argument to my dispatching function, just to make sure it could support those arguments. In other words, the dispatching function is going to be passed all the arguments to the function.
So if you had up to 5 arguments, the dispatching function would have to have 5 arguments.
No, it only has to name the ones it cares about. It can put the rest in a rest argument.
Okay.
Right? They'll be passed and just ignored. For instance, so it's perfectly possible to write a function that takes 5 arguments and really only cares about the first one. And it'll just say the first one and rest. And then the dispatch would be something that manipulates the first one and ignores the rest. Your dispatching function just has to be capable of handling whatever it's passed. So if you think it's going to be variadic, you put a rest argument on it. And you can also, it's a regular function. It can have arity overloading. That fun is a regular fun. You can do one thing when there's one argument, another thing when there's two arguments. This is really a general system. It's almost hard to imagine all the kinds of cool stuff you can do with it, but it's cool. All right. Yes.
Can you redefine method again?
Yes. Yes, you can. You can redefine methods. You can undefine them. And you can define defaults. I haven't shown you everything here, but yeah, you can.
Mention strings, for example, instead of the array. Can I put a string? It's like encounter and then some string.
Yeah, if that's a value that could be returned by this function. The thing is, this function really always returns a vector of two things. Right, but you could
like XML, for example, you would be parsing like sax, and you want to register if you get that tree, execute this function.
Right, you just have to be able to normalize it. But yes, your return values can be distinctly different. This function would be more involved in that case.
But it just has to return the tag string, and then you can put.
Right, you could just use. You could use strings. Sure. But for instance, just not to blow people's minds, but the dispatching function for a multi-method could be another multi-method. There's no problem with that, and there are reasons you would use it. You may have a multi-method that for instance, unifies classes and tags like these values to say, well, if it has a tag, that's the value. If it doesn't, then getClass is the value. That is, I think, will be a typical kind of a dispatching function, which is itself a multi-method. And then that becomes a dispatching function of another multi-method, which basically dispatches on tag or type. All right, so I've talked a lot about concurrency. Again, the number one strategy is to use immutable data structures. All these parts of Clojure go together. I like functional programming, and I like functions that take arguments and return new values and don't have side effects. But the way the persistent data structures work, and the fact that they are persistent and can be modified incrementally and efficiently, is also with an eye towards this concurrency support, as we'll see. So we start with immutable data structures, but Clojure is a practical language. I have never written a program that could have been completely functional. I think one of the functional programming guys had a great line. He said, if your program was really, truly, completely functional, the only thing it could do is warm up your computer. Because it couldn't have any output. Output's a side effect. And every program I've ever worked in needed some state that had to change, but much less than a typical Java program would generate just by using conventions. Yeah.
I wanted to say that warming the computer is also a side effect.
That's true. Maybe it is.
Well, you could set it up so it goes warmer to put top 1 and 0.
There you go.
But properly optimizing the compiler will take that away.
That's right. Yeah. So Clojure is practical. I'm not advocating or pretending that programs can be purely functional. I think some can. I think theorem provers can. I think programs that are fundamentally calculations can. Compilers can. Mostly, they have to spit out their results, but they can be mostly functional. And when you look at people who love functional programming, a lot of what they're writing are compilers, theorem provers, and math programs, because it's a good fit. The kinds of programs I write, there's always a database, there's some nasty screen stuff, there's audio cards, and there's things in the real world, for instance, that need to have proxies in the program, and or data structures that need to be modified in sync. So the idea in Clojure is that mostly you don't have any ability to change things. You can't change local variables. All the data structures are immutable. I'm going to give you two things that you can change: refs and vars. They're both single slot data structures. They're like, they're references. They're just an indirection point. And you can change what's in there. But that's it. And they're predefined. They both have two very different strategies for supporting concurrency. Refs are about sharing access to something that will change. There are going to be multiple threads. They're both going to look at this table. That table might change. I need to put it in a ref because at some point one, the other, or both of these threads may look at and or change this shared table. Vars are about isolating change. In this thread of control, I'm going to accumulate some values through a nested, nasty tree structure, and maybe I'm going to skip through some code I didn't write, and I need the ability to return values from lower levels up to higher levels, but it's scoped inside a single call chain, which means that in a threaded environment, it's localized to that thread. Vars give you the ability to isolate changes within threads. So we'll look at these two things. Refs and transactions. The idea behind refs is that they can be changed, and that the changes made to refs are transactional. So this is an implementation of what is more generally called the software transactional memory system. The one in Clojure is pretty neat. It's a whole other 2-hour talk. But if you haven't heard of it, that's what you would look up, STM or software transactional memory, to sort of see what the space is like. The general idea is pretty simple. If you've ever done database programming, you sort of have the notion of code being atomic and isolated. You go and ask for something to happen in a database, it either happens or it doesn't, and it happens with integrity and independence from other things. There's an acronym called ACID, which applies to database stuff. The C and the D don't apply to in-memory things without constraints. So there's no consistency checking because there's no consistency rules, and there's no durability because it's in memory. So refs are atomic and isolated. Atomic means that everything you do to a ref inside the scope of a transaction, to any refs in that transaction, happens, or none of the things happen. So any assignments you do to those references in the scope of a transaction happen, all of them happen, or none of them happen. Isolated means while your transaction is running, if somebody else is trying to modify those same references, those same refs, you don't see that. You don't see the effects of any other transactions inside your transaction. Does everybody understand those two principles? So that's a lot like a database. The one difference between most software transactional memory systems and databases, including this one, is that these transactions are speculative, which means that the system will retry them automatically. Like if you go through and there's these 3 bank accounts and you need to make this change that reads this one, calculates something else, and changes those other 2 guys, and somebody else is doing a similar kind of thing that involves one or more of those same things, they may win. They may get in and make a change first. Because you want to see a consistent view of the world, you didn't, right? Because now things are different from when you started. Your transaction will be retried. Because there was a conflict, somebody else was manipulating the same things, they won, your code will be rerun from the top of the transaction. You'll examine the same logic. Maybe you'll find out, well, now you can't do this transaction because there's no money left in this account. Or you'll see the new account values and you'll do your transaction on the latest account values. But it means that in particular, you cannot do anything with side effects inside a transaction. Because your transaction will run more than once. That's the way to think about it. It will run more than once. But this is a beautiful thing. I talked earlier about it. If you've ever tried to write a program that had 100 things that could be shared in subsets that overlapped. Sometimes I do the prime numbers, other times I do the numbers below 50, and other times I do the Fibonacci numbers. Those sets overlap sparsely, and trying to do that with locking is extremely difficult. If you have a global overlord of your whole software program, they decide we're going to number everything and acquire all our locks in order. Well, then you can solve that problem. But otherwise, it's an extremely hard problem. In a system that's been developed incrementally, maybe some guys thought they understood the whole world and they did a locking strategy for these 6 things, and now somebody else comes and says, I got these 2 things and I need 2 of yours in my transaction. That is almost impossible to do correctly. Even with extensive code reviews, it's very, very hard. This makes it completely transparent. You never do locking manually. You never say lock. You say sync, which begins a transaction, and everything inside it works. So this is a nice example, and it highlights a few cool things about Clojure. One is Clojure is pretty well integrated with Java. For instance, I don't want to get involved in thread startup and execution frameworks and things like that. Java, util concurrent, actually is very good. It has some really nice tools for thread pools and tasks and task management and things like that. All Clojure functions are callable, which means they can be put in these task lists and managed by the executor framework. In addition, all Clojure collections implement the collection interfaces, which means you can pass a vector or a map to a Java function that wants to see a list, or a collection, and it will just work. We don't have a lot of time to look at this, but this is just a hammer on the STM program. It takes how many items do you have, how many threads do you have, how many iterations do you want to run. It's going to make a map of references. It's going to map the reference function, which creates a reference, around a set of zeros. So you're going to have a bunch of references to an integer 0, as many as you ask for items. It's going to make an executor, which is in Java util concurrent, which is just something that runs tasks in a thread pool that has a fixed thread pool with the number of threads requested. That's all Java stuff. It's beautiful. It's very nice. Then we're going to set up a bunch of tasks, which are just going to be functions, lambdas. We're going to map this function over the range of threads. So we just have incrementing numbers, 1, 2, 3, 4, 5, 6, 7, by saying range. So range 7 says 0, 1, 2, 3, 4, 5, 6. So we're going to map this function that takes that number and makes a function which, in a loop for the number of iterations, creates a transaction. That's what sync does. Goes through all the refs and increments them by its number. So when you set up a bunch of threads to do this, you're pounding massively. Every thread is trying to do the exact same thing to the exact same data. Hammering on it, trying to, in a transaction, go through the entire list, which means they're going to need to temporarily lock everything in the list and modify it. Then we ask this executor, this thread pool, to invoke the tasks. Now, invoke all takes a Java collection, but tasks, which is the result of the map function in Clojure, returned a data structure, a Clojure data structure that implements that Java interface, so it's transparently passable to this Java function. And I'll talk more about this. This is the syntax for invoking Java. Dot, the object, the target object, the member function, and the arguments. So this is Java. This is calling Java, calling Java. Same thing up here, calling Java. Static function of the class. So we invoke the task. They run in separate threads. We ask the pool to shut down. This invoke all won't return until the tasks have completed. And then we're going to map this dereference bang you're allowed to call outside of a transaction. All other operations on refs must be in a transaction or they throw exceptions. So you can't read a ref, set a ref, mutate a ref in any way, except in a transaction. The deref is the only thing you're allowed to do to a ref outside of a transaction. It basically says, give me a wild look at the latest value, no matter what's happening. But it's convenient. And what happens? We test this. We run 10 items, 10 threads, trying to take 10 items and increment them with their number 10,000 times, and this works. It only takes a few seconds to do this. I know that's probably a lot of alien-looking code. Does anyone have any questions? The basic thing is sync. Sync starts a transaction. The body of sync will happen atomically. Yeah?
What's the purpose of nil?
Eventually, I'm going to have arguments to sync. Let's go away. I didn't ask for that, did I? Stop. This is the slide I want. Thank you. Eventually, but not yet, you'll be able to pass to sync some thread control parameters, like some timeout values and retry count values. Will be a map argument to sync. It's not currently supported, but that's the space for it. So you can say sync max timeout, 2 seconds, max retries 500.
I want to clarify. So you have your 10 zeros. Those are 10 separate 10 separate memory areas.
Correct.
So this is not one of those cases like your bank account where there's any conflict for the same one.
Yes, there is, because everybody's trying to go through that. In the transaction, this goes through all the refs. So every transaction is a transaction of take every ref and increment it.
So there are 10 threads. Each thread tries to increment 10 zeros.
For each time through this.
Good.
Right.
Okay.
Yeah.
So that's why you get the 55 coming out.
Yes.
Okay.
Yes. Okay.
Nice.
Yeah, the math is okay too.
Okay. How many times does it retry? Because when I tried it failed. It gave me a different answer.
Did you send me the message?
Yeah.
It retries like 1,000 times.
Okay.
So again, I'm not sure exactly why that's happening for you. It's working correctly because it's telling you I've retried max. But I think what's happening on that VM is it's not fairly scheduling the threads. So some thread is just sitting out waiting, never getting there are calls inside, there are locking calls that wake up the waiting threads. If they never randomize who they wake up.
Maybe thread dumps and see what's going on.
Yeah, it's possible. What you should try is this now example of parallel map up there, which is a more realistic thing that actually does some work. But one of the problems with this is, these are all spin loops, effectively. They're not doing any real work. You shouldn't expect this to work. You shouldn't write programs like this and expect them to work because there's too much contention. This is not a good design. This is just, does it produce the right result? Which it does. And in fact, if it tells you, I've retried 1,000 times and given up, that's still a correct result. Unfortunately, you don't have the ability to pass something in here when you can try 10,000 and see if that works for you. Maybe your machine's just faster than mine. I need to up the default. Any other questions? I think there were a few, right? Yes?
I'm just curious. Sync never deadlocks in isolation?
No.
That would never happen?
No, can't deadlock. Cannot. I promise. If it does, you can file a bug report. But no, it's very hard. But it's an incredibly interesting thing. This STM it implements snapshot isolation with multi-version concurrency control. So if you're familiar with multi-version concurrency control from like Oracle or Postgres, it's that way, which means every transaction effectively sees the world as of a particular point in time. And if other changes are made, they're stacked on top of that so that you can still see old versions, which means reads never block writers. Reads are always okay. And the history queues for the references dynamically will grow. So if in your program there's a lot of read contention for old values of a thing, its queue will actually grow a little bit. It starts off at 1, but it will grow to accommodate whatever your behavior is in your program. So it's pretty neat, which means that already you'd have very minimal locking because no reads block writers. In addition, the concurrency, the STM supports an operation called commute. So if you know the operation you want to do is commutative, like when I'm done with this, I just want to up this counter. It's better to say commute this thing with inc, which is the increment function, than to say counter equals counter plus 1, because that's a read, modify, write. And that has more locking contention. Commutes, they don't lock, because they don't need to lock until the very last instant. They'll work on whatever the latest value is. If it's 17, it'll be 18. If it's 19, it'll be 20. If you just want to commute a value. So it supports commuting. It has retry timeouts. It blocks threads in order to make sure the threads that are doing work complete, so it's not spin locking. It's pretty cool. It took me a long time to make. It's still a research topic, but Clojure's STM is unique. One of the things about it, though, is it's very much oriented towards these persistent data structures. If you read the STM literature, what you'll see is a lot of people trying to build, for instance, a red-black tree around STM kind of cells. This is not really written to do that. If you just put integers in like this, you're not going to have a happy day. The beautiful thing about Clojure is it gives you these nice persistent data structures. So you can stick, for instance, a reference to a map into one of these refs. So what happens? Two threads go and try to add something to the map. Well, they need to now speculatively make a change. Well, that's really cheap. First of all, the copies are free because there's no copying. They're immutable. And if I put something in my version, in my thread, my speculative transaction, and you do something in yours, that incremental change is also cheap because these are persistent. So a tiny change is a tiny amount of work. One of them is going to win. The other guy's going to need to retry it, but that's very efficient. That speculative clashing, I might change what is effectively a big data structure thing, is fast. So you really should be putting the full Clojure data structures in these references, and it will work well. Any other questions? All right. Bars should be a little bit easier for this audience. They're like special bars in Common Lisp, except they have thread semantics well defined. So what does that mean? They have dynamic scope, right? They can be dynamically rebound to values. They can be modified in the scope of a call sequence. They obey a stack discipline, which means as the calls unroll, the values pop off and the bindings unwind. The trick about them is that they're thread locals, so they really have well-defined threading semantics. They're isolated between threads. Effectively, whenever you say def, which we saw a bunch of times, including defun calls def, you're creating a var in the global namespace. That root value, the root binding, is shared. That's the only effective global mutable thing in Clojure. And you can leave it unbound. You could say def x, which means anybody that tried to access that without having binded it in a thread, it'll fail. Or you can put a value in it, in which case that value is shared. Def establishes those root bindings. Inside a local call context, you can use the binding primitive, which is like let, except it's not let. Right? In common Lisp, you can bind special variables in let along with local variables. I don't support that. You have a separate construct for that, which is this binding. But it's like let. You say binding this global thing to be 5, do this work. And in that function and all the functions it calls, 5, the cell for 5 will be the value of the binding. You can set that, which means you can modify it in the lower part of the call chain and see that back up as it unwinds. Once you pop out of the binding construct, the var is gone. That binding of the var is gone. One of the extremely cool things about Clojure, though, is that functions are stored in these vars. It's a Lisp 1, right? Which means all functions are stored effectively in special variables, which means all functions can be dynamically rebound. That's an extremely cool feature. That's one of the things I really worked hard to make work in Clojure. That means you can do things like, if you've ever read the guy's Context-L papers, doing context-oriented programming or do aspect-oriented programming, where in a certain call chain, in a certain context, when certain things are going on, you'd like to add a logging to a particular function whenever it's called. You can do that. You can just make a binding for that function, which is wrap the old function in some logging code, and then call it to this thing. Other threads that are calling the same function won't see that. They won't start logging suddenly. So functions can be rebound dynamically on a per-thread basis. That's an extremely powerful thing. You can do aspect-like programming that way, and certainly context programming. If you look at the guy, what is this, Pascal Costanza? Does anybody know? Is that the right guy?
Yeah.
Right. If you read his papers, I mean, he actually worked a lot on trying to put functions in special variables. That's the default in Clojure. Now I put this on the JVM, hopefully for a reason. One is that there's this huge library in Java that we'd like to be able to consume. And all the stuff you would expect to see in Clojure is there. You can instantiate objects with new. You can access members. You saw the dot operator before. The basic syntax of that is, dot, target, and then either field or method. The target could be an object, in which case it's an instance field or method, or a class name, in which case it's a static field or method. And that's how the calling works. It's worked out pretty well. I've done a few interfaces from Common Lisp to Java before. I did JFly and Foil and played with a bunch of different syntactic things. I like this one the best. There is type inference inside Clojure, so that, for instance, if you say, let x equal new executor, for instance, in that code before, the compiler will know that x is an executor, and if you issue any dot operations, there'll be calls to executors function, and no runtime method lookup will occur. In other words, that type awareness gets propagated through, and if that function, you call a function of executor and it returns another thing, the type of that will be remembered. So there's some inference so that the calls to Java avoid reflection. If I don't have enough information, the calls will be reflective and they'll work if there's a function with that name. But in general, it tries to be fast. You can import classes with import. We saw that. You can extend Java. You can implement interfaces directly in Clojure. There's an implement macro that allows you to implement an interface on the fly with lambdas being the bodies of the interfaces, and that works. And here's an example of swing programming. So we're going to import a bunch of swing stuff, frame, JLabel, JFree, all these things. This is the package name and then the classes from that package. It's pretty concise versus a line apiece for Java if you want to specify them. We're going to make a function. Here's frame. It's a new. So this is new. This is syntax in Clojure, special operator new. Class name, arguments. It will remember that frame is a JFrame. New text field, some buttons and pieces I want to put up on the screen. Yes?
For the new, don't you need to have the dot first? Or?
No, new is a special operator.
Okay.
So new is...
It's magic.
It's magic. New is magic. New class name constructor args is a special operator in Clojure. Dot is a special operator in Clojure. New is a special operator. Class, there's a couple related specifically to Java support.
Is there the difference between a static, an object that you instantiate versus a static method of an object?
Well, you'll have had to have told me that the name is the name of a class. So if you then said dot JTextField something, I would know JTextField is the name of a class, in which case that's a static member. Otherwise, it will presume that the thing after the dot is an object, and it's an instance member. And then we're going to say dot to the convert button, which it knows is a J button. So when this generates code, there will be no reflection in this code, just because it copped the types off of these initializations, and it will know the types of everything else. There is a way to supply type hints. If I couldn't know, or you're getting a return value from something else, and there's no way for me to know, you can tell me. So we ask the convert button to add an action listener, which requires something that implements the action listener interface. We can do that right here. Implement action listener. It has one function, action performed. It passes the event, and then we do some stuff to calculate the new, the conversion, and put that in the text of that thing. Do to is a nice macro. It just says keep doing the stuff to this object. It's as if you said dot frame set layout, dot frame add, dot frame add, dot frame add, dot frame. And that's why we use Lisp, right? That's a pain. First time I did it, I was like, I'm not doing this ever again. Do to macro, done. That's the beauty.
I have a question. Since this has a temperature, is this meant for interfacing to functional code via thermometer attached to the computer?
No. We warm up the computer with infinite loops. So do to is just a macro, and it just makes it easy to call a bunch of functions on the same object over and over. That's one of the nice things about Lisp. You don't have to wait for me to do that. If you wanted it, you could have done it. If there's some pattern you get annoyed by having to repeat over and over again, you can fix it. This is the nice thing about Lisp. You don't have to wait for the language developer to solve all your problems. And then we can go do the thing. Actually, I can do this one. I think, can I? Oops. Why does it do that? Actually, you know what I'll do? I'll just escape out of this. Here. We'll go to the app, and we'll just pop that in. Celsius, and here's my Celsius converter. What the ranges are. There you go. So, everybody see that? There's your swing.
Try 1453.
All right, back to the presentation. No. Yeah, I'm sure it does something. Probably not too pretty, but I'm sure it calculates something. So this is cool. This is this much Java when you write it in Java. So it's much shorter. Any convenience stuff you want to do. You have macros. You have syntactic abstraction. Anything that you have to do over and over again, you can make go away. That's the point of Lisp. And the cost is some parenthesis, and it's worth it. Most people in the room think it's worth it, or they wouldn't be hanging out here after all these years. All right. What else can we do? Well, there's a lot of integration in the types of Clojure things. Clojure strings are Java strings. They're not like a different thing. They're immutable, so I don't have any issues like you would have with common Lisp strings because they're mutable. Clojure strings are Java strings. Pass them, get them back, they're the same thing. Clojure collections implement the mandatory portion, which happens to be the read-only portion of the Java util collection interface. So Java function takes a collection, you can pass a Clojure thing directly. Clojure functions are callable, which is a no-arg thing that's used by that executor framework, for instance, to start threads and run things in threads. So if you have a Lambda and it takes no arguments, you're ready to go. You don't need to do anything. You need to package it or call a new thing or do anything. It's there. Symbols and keywords are comparable. And everywhere I could where it made sense for my types to integrate with the Java types, they do. So that works easily. In addition, Clojure implements and emits the standard JVM debug info, which means that, for instance, hopefully I can find this one. This is JSWAT. This is a Java debugger. I didn't touch. I said start Clojure, and down here this is some Clojure code. I called the select function from Clojure, which takes a map and pulls out a couple of keys from it. This is the Clojure code over here. I put a breakpoint here. I can run to the breakpoint and stop there. Where am I? It's been running for a while. Maybe I can after waking up from sleep. Hello. I put this to sleep before I drove down here. I should have tried it once before. Alright, this guy's totally hung. Can I get anything? No, see, its UI is hung. Oh, I wanted to show you this. Well, you can sort of see over here that the locals, this app is hung, but the locals are visible here. So I can set breakpoints, I can single step, I can see the local variables with the names that were in Clojure. This is Clojure code that this generic Java thing is able to do. I've tried the same thing in NetBeans and Eclipse, and they don't work as well. Let me see if this thing, I can just do this. Probably won't even respond to that. You gonna give me a force quit? Oh, except I don't know which Java this is. I don't want to kill my other thing. Alright, I won't spend time on this now. So the debug story is kind of cool. This is the way it should work, right? This bytecode has the right debug information. It has line numbers that correspond to Clojure lines. It emits the names of the Clojure variables. But like NetBeans and Eclipse, if the bytecode doesn't map to Java, they have like Java extensions hardwired in the IDE source code in places. So it's hard to make them do the right thing. And this JSWAT has been the best so far. So there is potential to do debugging because of this. So where am I at? It's currently alpha. It's on SourceForge. It's open source. I think I said that about before. You can get a download, which has a jar file you can just run, and the source code. Everything I've talked about is working. So this is not a slideware thing. Yes?
What license is it released under?
It's under the common public license, the one that Eclipse was originally written under. So it's a non-viral. I think it may have some GPL incompatibilities, but I'm open to input on that. But so everything I'm talking about works. Do you have a question?
Yes. I'm not that familiar with Java, except that I tried BRL once and I found error output too voluminous, too much. Is that a problem here? You get too large error messages?
Well, right now, because I'm in alpha, I am taking the full stack dump here. So, it doesn't know what this means, and I get that. I'm going to make it so that you're going to get the exception method, and there'll be a flag you can set that will tell you whether or not you get the full stack dump, and the access to the stack dump. So that'll give you smaller
So in the meantime, you
things.
concentrate on the top of the dump?
Well, it depends. If you're me, I have to figure out where the problem is. In this case, you would only, as a user, this first line would be enough, right? I don't know DSAKJH, and then you say, oh yeah, I never defined it. Clojure is actually pretty strict about that, more strict than Common Lisp in terms of flagging use of names that have not been previously defined. It's not okay in Clojure. You have to def them at least. Because you can def them, it doesn't create any root binding or anything. So if you need to do something with circular references, that's all you'll need to do. Let me just finish my slide and then I'll finish the questions. We'll have general QA. So everything I've talked about works. The main reason I'm calling it alpha is mostly because I'm still maybe change some names. And so when it's beta, I'd probably rather not do that. Not that I never would, but that's mostly what it is. I'm enhancing things, mostly enhancing the documentation. But there are a lot of docs. You can go on the website, but there's documentation of all kinds of things here. How the reader works and all the functions. I mean, there's a lot of documentation, but there's a lot to document. I think as Lispers, you'll be better off. One of the problems I have is part of documenting Clojure is actually explaining Lisp to people, and that's its own project. So I've done less of that and more of like the things that make Clojure unique and the integration. And so some people that don't know Lisp are struggling a little bit, but I'm still working on that. I just showed you debugging frozen in JSWAP, which does work okay. But to do, there's plenty of library functions I haven't yet written. There's library functions I've written I haven't documented, and that stuff's coming along well. You can see though, I want to show you real quick this is the bulk of Clojure library. I mean, it starts up, it doesn't know how to do list, cons, conj, defun, anything. This all gets bootstrapped when you first load it. It reads this file and creates the rest of the language. And it does that in quite a hurry. You can also see how small most of these functions are. Commuting, this is all the stuff for references, the sequence functions. There's partial apply here, any, every, here's map, lazy map. That's pretty small for a lazy map that has, that's overloaded on one map or multiple maps for efficiency without having to do a conditional test. And you can see how neat it is that the multiple map version calls the single map version in the same function object. Filter, see, these are very small, and a lot of these are lazy. Just so you get an idea of the perf, so that's called boot.clj. That comes up every time. I don't know where that is. Is it right here? It may not be right here. Nope. Do I have any typos? I didn't even look. So that's like loading the whole language over again and recompiling it.
Do you have time?
Yeah, you have time. Well, considering the REPL really, it really does compile whatever you do. So, just so you know, it's real. I haven't shown you a lot of interactive because it's just time limited, but so there's more library functions I want to add, but they're pretty small, and I think it's a nice language to write in. The functions you end up writing are elegant and clean. It's like the best of Lisp and the best of Haskell, kind of. I want to add support for extending classes. A lot of Java libraries require you to extend concrete classes as opposed to interfaces, which I think is hideously wrong, but they do. So you need to be able to do that. So I have to add that capability. The editor story is the one that I feel I need the most work and possibly help with. There is no editor that knows about Clojure yet. So trying to do that.
Slime backend? Yeah.
I don't know enough about it, but that would be neat. Slime would be neat. Anything for Emacs would be neat. I've looked at doing NetBeans a bit. One of the appeals of trying to leverage a Java IDE is that one of the things I'd like to be able to do is completion on the Java libraries. That's the already solved problem in those spaces. So I played around with NetBeans. It has like a Schliemann module for doing syntax extension. That works okay, but it's still not great. It's kind of slow. The debugging story, again, JSWAT works, but I'm very disappointed that NetBeans and Eclipse don't do as well as JSWAT, which is, JSWAT's actually built on Eclipse, and it works, and built on NetBeans, and it works, and NetBeans doesn't work. It doesn't allow you to set a breakpoint in code that doesn't have .java at the end. And then, fit and finish and performance tuning.
Like
Yeah, it's like hardwired 6 or 7 places in the source for NetBeans.
If you just named the files .java and you put.
I don't know. That would be that might work. I haven't tried it. That might actually work. The thing is, I have a feeling that when it sees that, it's going to then try to do some interpretation of the syntax.
Which clearly
that will not work. JSWAT seems to not care about that because it's not otherwise an editor.
Right.
It just basically does breakpoints and step. So this is the website. That'll give you all the docs and everything else, and you can get to the downloads from there. You can also go through that to get to the discussion group, which is on Google Groups. Thank you. And any questions? Yes.
You didn't mention any conditionals or exceptions.
There's if, there's con, there's try and try finally. I'm still working on try catch, so that's on my to-do list. But there's try finally, and so therefore there's the same thing as unwind, protect stuff.
You've obviously put a lot of work into this. Is anyone sponsoring you to
No,
do this? Or is it just in your free
I
time?
spent the whole bunch of my own money to do it. Yeah, at least to get it bootstrapped. Now it's strictly part-time, so any other contributions or help, it's going to move a little bit more slowly. But I've been working on the design for 2 years, and incrementally working on the code, and then I really took the summer and built it, and made the transition from source code generator to a real bytecode compiler, and finished, a core. And now it's Lisp, so everything you do from now is in Lisp in Clojure, so it's fast.
Do you have any commercial projects that you're looking to use Clojure on?
Yeah, my own. Yes, I definitely hope to be able to do the programs I normally write in Clojure. That's the objective. And it has the ease of approachability of a scripting language, but it's a real programming language that I could use to replace Java in places where I would have to use Java.
What type of programs are those?
Automation systems, scheduling systems, audio analysis, and things like that.
How's the quality of the output in code compared to, like, when you in GUI apps it wouldn't really matter so much, but in scheduling systems I assume there'd be some.
It's good. I mean, the main I talked earlier. I'm not sure if you were here, but the direct calls to Java code where I have enough information to do type inference, either I saw the new of the value or you gave me a type hint, are exactly the same code Java would emit. It's push the args, direct call. I don't use reflection. If I don't have any information, then you get a reflective call, which again for UI programming won't matter at all. The main difference from a pedal to the metal standpoint between Clojure and Java would be numerics, because all Clojure numbers are boxed. So it's never going to compete on that. But
cryptography probably.
No, but the thing is, I really don't feel like it's something you would need to apologize for to write part of your program in Java. It's so easy to consume it. It's going to be the right thing to do. And to make a language perform well and be as dynamic is very difficult. I mean, if you've tried to write Common Lisp and make it really efficient, by the time you get all those declarations in there, it's not that elegant, pretty Lisp you had before. And so my approach is, I'm not gonna bother ever trying to have primitives in Clojure. And if you have something that you need to do, you can write a little Java and then call it. And it's really pretty simple. Otherwise, the performance is excellent. And just so you know, the data structures are generally within a factor of 4 of the Java data structures. So they're persistent, immutable, have all those benefits, and they're never more than 4 times slower. And of course, the Java stuff would be a lot slower if you had to lock it and use it in a multi-threaded program. All of a sudden, any performance advantage there would be gone. And many times they're as fast or faster. For instance, the hash table lookups are extremely fast.